Hello.
Q point.
DC load line.
Yeah, DC load line, right? DC load line, right? So DC load line is for what? DC load line is for what? It is for a which configuration we have seen? Common emitter configuration, right?
Yes, sir.
Yes,
Okay.
sir.
Yes, sir.
So common emitter configuration, I will just draw. So let us say this is your transistor. This is emitter, base, collector, right? So always which transistor we are using? N, P, N. And then how we have biased it? How we have biased it? So we have connected. So this is P to P, forward bias, right? Base emitter should always be in forward bias. N to negative. And similarly, collector base should be in reverse bias. So this N we are connecting it to
Positive.
Positive.
positive, right? And this I'm connecting it to a common terminal. Let us say that it is connected to ground, that is 0 volts. Okay. Let us say that this voltage which is applied to the base is VBB,
BBB.
and let us say this voltage which is applied to collector is VCC.
VCC.
Okay. There is one more voltage between base and emitter. Let us say that it is plus V between base and emitter, VBE. Okay. Similarly, there is a voltage between collector and emitter. This voltage I will call it as
VCE.
VCE, right? Now there will be some currents which are flowing in the transistor. So let us call it as IB. Let us call this current as IC, and let us call this current as IE. Okay. So whenever you are referring the PPT, okay. So one notice, right, that I have shared the PPTs, right, which are there, right. But in the PPT is always the current direction that is given ulta. Okay. So that current direction which are mentioned in the PPTs, right. So that current directions are the that is not the current actually. That is the direction of flow of electrons. Okay. So please note that. And second thing is that whenever you are learning this unit number 2, I will specially say that you just follow the sequence in which I am teaching to you. Are you understanding these concepts of transistors?
Yes,
Yes,
sir.
sir.
Yes,
Okay.
sir.
So
Yes,
please
sir.
follow the same sequence while studying also, else you will get confused. Okay. So let us go back here and let me start this thing. Okay. Now what is the input current? What is the input current? IB. What is
IB.
IB.
output
I
current? IC.
I
IC.
Right?
see.
Okay. Now there was something which I have connected here, right? There was something which I have connected here, and that we can call it as, yes, that we can
RS.
call it as
Register.
a resistor.
RB.
And some resistor was here also. Okay. So this resistor is your RB. This resistor is your
RC.
RC,
RC.
RC.
right? So both are
RC.
called as your current limiting resistor. Now we can always apply a Kirchhoff's voltage law in loop number 1, and we can call it as let us say that this total applied voltage, I will just call it as by Kirchhoff's voltage law, and I can say that this VBB, total applied voltage, is nothing but some voltage will get drop across this RB. That voltage I can call it as IB into RB, and some voltage will get drop across this base emitter junction. So I can call it as VBE,
VBE.
right? And from here I can take out the value of IB. So this IB is nothing but VBB minus VC,
VB.
VBE,
VBE.
right?
VBE.
VBE,
By
right?
RB.
Divided by RB. Okay. Normally we are using silicon transistor, right? So for silicon transistor, this VBE is 0.7 volts, right? Any problem in this?
No,
No,
sir.
sir.
No, sir.
Okay. Similarly, there is another battery, right? So I can apply again one Kirchhoff's voltage law here, and I can say that this VCC is nothing but some voltage will get drop across
ICRC.
this RC. So that is ICRC plus
Plus
some voltage
BCE.
across collector and emitter, right?
Emitter.
Emitter.
So this was your equation number 2. This was your equation number 1. Any problem in this?
No, sir.
No,
No,
sir.
sir.
Okay, and then we have a DC load line, right? So DC load line हमने निकाला था. It was like this, something like this. Okay, So I will just can you see this thing, or shall I maximize it? This is fine, I guess, right?
No, it is fine, sir.
Okay, okay. So DC load line, we have drawn something like this, right? And it was drawn on the output characteristics, right? So output characteristics of your collector emitter junction, that is, it is a graph of what? VCE,
I
output voltage,
This
versus
current, I
output
see.
current, right?
I see.
So that is IC, okay. And then you are getting a DC load line like this, right?
Yes, sir.
And
Yes, sir.
we were getting a Q point, right? So always the Q point was at center of the DC load line, and I can call it as Q. Okay. Now see, can I say that Q point, जो ये जो point है, this point is on the line, right? So can I draw the coordinates of this Q point? Can I draw the coordinates of this Q point?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes. So let us say यहाँ पर कुछ voltage available होगा. Let us say इसका कुछ value होगा VC, and let us say इसका भी कुछ value होगा IC, right? So हम कोई भी point जो है वो XY axis पे कैसे denote करते हैं? A x comma y, right? So this is x. X is your VCE, comma IC.
I see.
Getting? So Q point आपको अगर पूछा जाएगा तो what you want? You want the value of VCE as well as you want the value of IC. Getting?
Yes, sir.
Yes,
Yes,
sir.
Okay.
sir.
Corresponding
Yes,
to
sir.
what? Corresponding to some constant IB, और IB का वैल्यू क्या रहेगा? IB का वैल्यू रहेगा ये वाला. Okay. So I will draw a graph of IB, right? I will draw a graph of IB. Okay. So Q point is of course the intersection point of your output characteristics, right? Keeping IB as constant, right? और ये constant value कौन सा लेना है? ये लेना है. यहाँ से जो वैल्यू आएगा ना इस इक्वेशन से, वो लेना है. ओके. अभी देखिए Q पॉइंट, अगर Q पॉइंट कट ऑफ रीजन की तरफ जाएगा, कट ऑफ रीजन कहाँ पर है? कट ऑफ रीजन कहाँ पर है?
सर ऊपर
दिस इज
या
योर कट
नीचे?
ऑफ रीजन, राइट? एंड यहाँ पर किधर तो भी सैचुरेशन रीजन है, राइट?
Yes,
Yes,
sir.
sir.
सो
यस
Q
सर।
पॉइंट अगर कट ऑफ रीजन के पास जाएगा तो आप इनपुट में क्या दे रहे हो ट्रांजिस्टर के? व्हाट इज योर ट्रांजिस्टर? बेसिकली एम्पलीफायर क्या होता है? व्हाट इज एम्पलीफायर? इट विल एम्पलीफाई द सिग्नल, राइट? सो लेट अस से व्हाटएवर आई एम स्पीकिंग, दैट इज योर AC सिग्नल, राइट? सो दैट व्हाटएवर आई एम स्पीकिंग, दैट इज योर AC सिग्नल. सो दैट AC सिग्नल विल गेट एम्पलीफाइड, राइट?
यस सर।
ओके.
Yes,
सो
sir.
देखिए मैं बात कर रहा हूँ, और वो AC सिग्नल पूरा का पूरा एम्पलीफाई होना चाहिए, या you want something which will get means distorted होना चाहिए, या faithful amplification होना चाहिए?
Faithful
फेथफुल।
amplification.
Faithful
Faithful
amplification, right? So
amplification.
अगर Q point कट ऑफ की तरफ सरकता है तो फिर क्या होगा?
There will be no faithful.
नो।
There will be distortions, right? और अगर
यस
Q
सर।
point saturation की तरफ सरकेगा तो क्या होगा?
तो भी
Again there will
Faithful
be some
There will be.
amplification.
distortions, right?
यस सर।
उसके बाद में अगर IB है, राइट? अभी देखिए, let us suppose ये VCC है. Okay, I am giving some values, right? VCC is 15 volts, VBB is 5 volts. Okay. तो अगर सुनिए, तो आउटपुट वोल्टेज मैक्सिमम कितना हो सकता है?
5.
हाँ, आउटपुट
Uh,
वोल्टेज. देखिए, मैक्सिमम वोल्टेज आउटपुट कितना हो सकता है?
15 volt.
15
15
वोल्ट ही हो
volt.
सकता है ना.
15।
बराबर है, बिकॉज हम ज्यादा से ज्यादा इनपुट कितना दे रहे हैं? मतलब सी एम्पलीफायर तो खुद से नहीं करेगा, राइट? इट विल टेक सम एनर्जी, राइट?
Yes, sir.
Maximum energy, how much in terms of voltage? Let us say how much I am getting? 15 volts. So
15.
15 से ज्यादा तो नहीं देगा वो आउटपुट वोल्टेज, राइट?
No, sir.
Getting?
No, sir.
तो
Yes,
एक
sir.
सिंपल एग्जांपल लेते हैं, राइट? लेट अस से इनपुट इज 5 volts, राइट? ओके, इनपुट इज 1 volt and gain is 3, so output will be 1 into 3, output will be 3 volts, right?
3
अगर
volt.
इनपुट 4 है, so 4 into 3 12 volts. अगर इनपुट 5 है, 5 into 3 15 volts.
15
अगर
volt.
इनपुट 6 हो गया तो फिर आउटपुट कितना आना चाहिए? 18 volts. दे पाएगा?
No, sir.
No,
नो.
sir.
नो सर।
व्हाई? बिकॉज हमारा जो
There
मैक्सिमम
is a limit
वोल्टेज वही
15.
15 volts है, राइट?
15.
गेटिंग? मतलब अगर इनपुट में हमने, लेट अस सपोज, अभी करंट की बात कर रहा हूँ, इनपुट में अगर करंट बढ़ाया तो भी प्रॉब्लम है ना.
Yes, sir.
Getting?
Yes, sir.
Okay. Now I'm just trying to tell you, I'm trying to tell you two words, one of which is faithful amplification, right? One of which is faithful amplification. Now see here, the thing is that we will just go to this slide, and here we can see that what is your linear operation, right? So linear operation matlab kya? What is equation of a straight line?
Y equal to mx plus
Y is
c.
equal to mx plus c. Okay.
C.
सो मैं ये बोल सकता हूँ लीनियर एम्पलीफिकेशन मतलब क्या, इनपुट में 1 वोल्ट, आउटपुट में 2 वोल्ट, इनपुट में 2 वोल्ट, आउटपुट में 4 वोल्ट, इनपुट में 3 वोल्ट, आउटपुट में 6 वोल्ट, राइट? सो with respect to input, your output is linearly increasing. With respect to your input, your output is linearly increasing, right? So what is linear operation? I can say linear operation is nothing but when your transistor will give your output which is linear with respect to the input, that is your linear operation, correct?
Yes, sir.
Yes,
Yes,
sir.
sir.
So we should have a linear operation, बराबर है? So linear operation हमें कहाँ मिलता है? So we will get the linear operation of the transistor in the active region, right?
Yes, sir.
Yes, sir.
So we should operate the transistor in active region. Active region कहाँ पर है?
Top left.
Active region कहाँ पर है? When the Q point will be in the center of the
Center.
Center
Center.
of the DC load
DC
line.
load line.
okay, okay, good. So now let us say that distortion कब होगा? Whenever this Q point, can you see this is shifting towards?
Saturation.
Correct.
Okay. Now सुनिए, इनपुट कहाँ पर होता है? इनपुट कहाँ पर होता है? What is input? Can I say input current? Right?
Yes,
Yes.
sir.
Yes, sir.
Input current
Yes, sir.
होता है, right? Correct. So can I say this is IB? Okay, I will change the color. Can I say this is IB? Input current, right?
Yes, sir.
Yes, sir.
Now, can I say IC? This is IC is nothing but beta times IB. Yes.
Yes,
Yes,
sir.
sir. Yes, sir.
Yes, sir.
Yes, sir.
And this is some output voltage. So this is output voltage, right? VCE, right? And VCE is what? VCE is what? VCE is what? VCC minus ICRC इक्वेशन में
Yes,
से.
sir.
सो
Yes,
इनपुट
sir.
करंट देंगे तो हम वोल्टेज भी देख सकते हो, करंट भी देख सकते हैं, राइट? नाउ हियर क्यू पॉइंट का ओरिजिनल जगह यहाँ पर था. क्यू पॉइंट का ओरिजिनल जगह कहाँ पर था? यहाँ पर था. यहाँ से क्यू पॉइंट शिफ्ट हो गया ऊपर की तरफ, राइट? मींस टुवर्ड सैचुरेशन रीजन. सो व्हाट इज हैपनिंग? द पॉजिटिव पीक इज गेटिंग क्लिप्ड ऑफ.
Yes, sir.
Yes. So this
Yes.
thing is called as your distortion, correct? Right?
Yes,
Yes,
sir.
sir.
Okay. Now, with respect to this, right? Now, Q point कहाँ पर था? यहाँ पर. यहाँ से कहाँ पर शिफ्ट हो गया? Q point
Cut
कहाँ
off
पर
region.
था? यहाँ पर. कट ऑफ की तरफ. कट ऑफ की तरफ अगर शिफ्ट हो रहा है, तो फिर क्या होगा? आपका निगेटिव पार्ट चले जाएगा. मतलब क्या होगा? The cutoff, whenever the Q point is shifting towards the negative or cutoff region, what will happen? The negative part will get clipped off, and that is called as your distortion. Yes.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
So this is again called as a distortion. Okay. So clear. And whenever Q point is, see, now Q point is in the center. Q point कहाँ पर है? सेंटर में. बट हमने जो एम्पलीफायर है उसका जो कैपेसिटी था, लेट अस से मैंने क्या बोला, 15 वोल्ट्स. ओके. सो जब तक इनपुट 5 वोल्ट्स है तब तक आउटपुट 15 वोल्ट देगा. जब आउटपुट अगर 6 वोल्ट्स हो गया तो आउटपुट में कितना एक्सपेक्टेड है? 18 वोल्ट्स, राइट? लेकिन
Yes, sir.
कब तक दे सकता है? ओनली टिल
15
15
volt.
वोल्ट्स, राइट?
15
सो
volt.
सपोज ये वोल्टेज है, ये 15 वोल्ट्स है. सो 15 वोल्ट्स के ऊपर जो वोल्टेज है ये तो कट हो जाएगा. मतलब अगर इनपुट का करंट हम ज्यादा दे रहे हैं ना, लेट अस से दिस इज 5 वोल्ट्स, ओके, सो 5 से ज्यादा दे रहे हैं हम लोग, राइट? सो व्हाट
Yes,
इज
sir.
हैपनिंग? ये जो दो पार्ट्स है ये क्या हो जाएंगे? कट हो जाएंगे. गेटिंग? सो अगेन दिस इज आल्सो कॉल्ड एज अ वेवफॉर्म डिस्टॉर्शन. This is also called as a waveform distortion. So this is the third case which we can say when the transistor is driven both in cutoff as well as saturation region because यहाँ पर देखिए क्या लिखा है? Because
Input
Input
signals
signal
is
is
too
too
large.
large.
Is
Is
too
too
large.
large, right? So for faithful amplification, we want to keep the Q point at the center of the DC load line, as well as we need to give the input signal which is in
Less
the
than
range
or
of
equal
Less
to
than the input
range
output
of operation,
voltage.
right? Okay, very good.
Yes, sir.
So this is regarding distortion, right? And next point we can say that this is your generic DC load line which we have seen yesterday, correct? Yes.
Yes,
Yes,
sir.
sir.
Yes,
Yes,
sir.
sir.
Now the sequence, right? Sequence, just keep it what I am teaching to you, right? Now this was the graph, isn't it, which we have discussed. We are discussing this from previous 3 lectures, right?
Yes, sir.
Yes, sir.
Yes,
So
sir.
this region is
Saturation
Saturation
region.
region.
Saturation.
saturation region, right? Okay, here current is very high. Can I say current is high?
Yes, sir.
Yes,
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 sir.
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 This region is what? Cutoff region.
Cut off.
Cut off.
Top
Here what is the
region.
current?
Zero.
Low.
Zero.
Zero,
Zero.
right? So what is the behavior? What is the behavior, right? What is the behavior? What is the behavior? Okay, so in cutoff region what happens? In cutoff region what is IB?
IB is equal
Zero.
to 0.
0.
So IC will be, सुनिए, कट ऑफ
0.
रीजन में both the diodes are in forward or reverse bias?
Reverse bias. Both
Reverse
Reverse
bias.
diodes
bias.
are in
Reverse
reverse
bias.
bias.
IB तो
Reverse
जीरो हो
bias.
रहा है, IB तो जीरो हो रहा है, तो यहाँ पर भी कुछ करंट है ना, वो फ्लो नहीं होना चाहिए. IC कितना होना चाहिए आइडियली? IC is also
0.
zero, right?
Zero.
Zero.
So there is very small current which is flowing due to minority charge carriers, right? And that current is called as ICEO, right? And the direction of the current is not like this. The direction of the current is from collector to emitter, right? So इसका
Yes, sir.
मतलब ये है, current flowing from collector to emitter, what is open? Base is open. समझ में आया?
Yes, sir.
Yes,
So
sir.
IB is equal to 0. The transistor is said to be in cutoff region. This is shown that with base open, the resulting current IB is 0, and whatever current is flowing, that is leakage current, nahi to reverse saturation current, which is flowing from collector to emitter, and when base is open, correct?
Yes,
Yes,
sir.
sir.
Yes,
Yes,
sir.
sir.
Okay. Now just see here. So if IC, can I say it is almost equivalent to 0?
Yes, sir.
So there will be no voltage drop.
Yes, sir.
Yes. Now, can I say that VCC is equal to VCE because both these are parallel. In parallel, voltage is same. In parallel, voltage is same, right?
Yes, sir.
Yes, sir.
Okay. So okay. Now second one is your saturation current, right? So saturation region में क्या होता है? Saturation region में the current is very high, right? Both the diodes are
Yes,
in
sir.
forward
Forward
bias.
bias.
Okay.
Forward
Forward
bias.
bias.
So normally for a voltage, this VCE saturation is 0.2 volts. VCE saturation is 0.2 volts, correct?
0.2 volts. Yes, sir.
Okay. Now there is one condition that whenever you will calculate, see here IB is present, IC is present, and you are having the equations, right? Okay. So when the transistor is said to be in saturation region, whenever your beta times IB is greater than the calculated IC. Yes. Hello.
Yes, sir.
Yes,
Yes,
sir.
sir.
So whatever I'm writing, that I will explain with the help of example, right? So आपको अगर पता करना है कि आपका ट्रांजिस्टर कौन से रीजन में है, right? Then what you will check, you will calculate IB, you will also calculate IC. IB और IC कैसे calculate करेंगे? By using the equations, right? And then you just check beta times IB. If it is greater than IC, then your transistor is said to be in saturation
Saturation
region,
region.
Saturation region.
right? So base emitter and base collector junctions are forward bias in saturation region, right? Any problem
Yes,
in
sir.
this?
No,
No,
sir.
sir.
No, sir.
Okay, okay. And how to calculate IB and IC? How to calculate IB and IC? See, again, I am saying that you need to ignore the direction, right? Because this is ulta and this is also ulta. Okay. So, how to calculate IB? We have the equation, right? So let us say this is plus VBE, right? So can you
From
calculate
Kirchhoff's
IB?
law. From
So,
Kirchhoff's law.
so VBB is equal to IBRB plus VBE,
VBB.
right?
VB.
So you just calculate IB is equal to VBB minus VBE divided by RB,
RB.
right? Similarly, how to calculate this IC? So I can say VCC is equal to ICRC
ICRC.
ICRC
plus
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 VCE,
VCE.
right? So therefore IC is equal to VCC
VCC minus
minus
VCE
minus
by RC.
VCE
By
divided
RC.
by
divided by
RC,
RC.
correct?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, okay. So this is your saturation, right? This is your saturation region. So this is how you calculate the region of operation of a transistor, right? Region of operation of a transistor.
Yes, sir.
Okay. Now, next. DC load line, you know. Okay. So let us have a numerical. Let us have a numerical. Now, what is this? Here you can just check that we need to check whether this transistor is in saturation region or not, right? And as told, VC sat is always zero point 0.2 volts, right? Now here is some voltage. Here is some voltage. How much is this voltage? If we consider a normal transistor, this is your 0.7
0.2.
volts, correct?
Yes,
Yes,
sir.
sir. Yes,
For
Two
sir.
point,
silicon.
yeah, because it is silicon, right?
Silicon.
Okay. Now, can we calculate IB? Okay. Can we calculate IB?
Yes, sir.
Yes,
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 sir.
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 So IB will be
Uh,
3 volts minus 0.7 volts divided by 10
10.
kilo.
10
So how much
kilo.
it is?
0.27.
0.4.
2, 3, right?
Yes,
Uh,
sir.
2.3, so it will be
2.3 by
0.23
23
milliamperes, right?
milliampere. Yes,
Yes,
sir.
sir.
Yes,
Yes, sir.
Yes,
correct.
sir.
Yes,
Yes,
sir.
sir.
Yes,
Yes,
very
sir. Yes, sir.
And what is beta times IB? Beta times IB, just multiply this by 50 because beta DC is given 50. So 50 multiplied by 2.3, how much it is? Is it 11.5?
1. Yes, sir.
yes,
11.5.
Yes, sir.
11.5 milliamperes, right? Okay.
Yes, sir.
Yes.
Now, can I calculate IC?
Yes, sir.
What is
Yes,
IC?
sir.
10 minus zero point 0.2.
0.2
Why
divided by
0.2? Because here the voltage is VCE and it is given that is 0.2 volts, right? Divided by RC, that is 1
1.
kilo. So how much it is? 9.8
9.8
milliampere,
milliampere.
Milliampere.
Yes, sir.
right? So can I say if you compare this beta DC, if you compare this beta DC with IC, right? Can I conclude that beta times IB is greater than IC?
Yes,
yes,
sir.
sir.
Yes,
So
sir.
therefore you can say that
Yes,
this transistor is in which region?
Saturation
saturation.
region.
Saturation.
Saturation.
Getting?
Yes,
Yes,
sir.
sir.
Yes,
Yes,
sir.
Okay.
sir.
Any problem in this?
No, sir.
No, sir.
No,
Yes,
sir.
sir.
Simple, eh?
Yes,
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 sir.
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 Yes, sir.
Yes,
Okay,
sir.
okay, okay. So let me rub it. Okay. Now, so this is the solution. You can see it later on. Okay. Now, just try to solve this question. The base current, what is given? IB. What is this? IB is 50 microampere is applied to the transistor and the voltage of 5 volts is drop across RC. Matlab what is given? What is this 5 volts? Can I say it is IC into RC?
Yes,
Right?
Yes,
sir.
sir.
Yes, sir. Yes,
Okay.
sir.
Okay. So IC into RC is there, right? And then determine beta DC of the transistor. We need to find the beta of the transistor, right? So can you calculate IC?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
First of all, what is this voltage? How much is this voltage? VBE. How much it is? 0.7 volt.
0.7 volt.
Yes, sir.
VBB दिया है VBB. VBB is also not given, right? So how to calculate beta? Yes.
Sir,
First we have to
IB का
calculate
formula
IC.
use कर.
हाँ, yes. First of all, we need to calculate
IC.
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 Very good. So can I say this is the voltage drop. This 5 volts is nothing but IC into RC. RC is how much?
1
1
kilo.
kilo.
So can I say this is 5 divided by 1 kilo? So it will be 5 milli
Ampere.
Ampere.
ampere,
Yes,
right?
sir.
5 milliampere.
Yes, sir.
Correct?
Yes, sir.
Okay. So therefore, can you calculate beta? Beta
Yes,
is
sir.
IC
I,
upon
I,
IB. So how much it is beta?
100,
10
sir.
5 divided by 50 milli micro. So it will become 100.
100.
Right?
Yes, sir.
Yes,
So
Yes,
समझ में
sir.
आया?
Yes, sir.
So
Yes,
this
sir.
is solution, right? Simple solution. You can just see it out.
Sir, check lobby, sir.
Yes.
There are some students in lobby.
But they should come, right? You can check my. No one is there, right? See, the thing is that I have a extension, right? So they will just it will just accept all the people, right?
Sir, there are message on groups.
Okay. So tell them to join. Okay. So shall I continue?
Yes, sir.
Yes, sir.
Yes, sir.
So there will be some numericals, some more numericals, right? So you can just go through that. Okay. So determine each current. So now I guess you can calculate IB here. Can you calculate IB?
Yes, sir.
Yes, sir.
Yes. VBB is there.
Yes, sir.
This is 0.7. So VB 4 minus 0.7, 4.3 divided by 4.7 that will
4.7.
be your IB. Right? Similarly, 24 minus 8 divided by 470, that will be your IC. And I will be IB plus IC. Right?
Yes.
Yes, sir.
Yes,
Is
sir.
it okay? And let me see, is there someone in the lobby? Yes. I guess. Okay. So you just check it out, this solution, right? Okay. So any problems? So can you calculate this thing now?
Yes, sir.
Assume that the
Yes, sir.
transistor in the circuit of the figure is replaced with one of the having beta is equal to 200. Can you calculate all these things? Yes?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. VBB, VCC are given. Okay. Now, very important thing. So how many configurations we have seen?
3.
3.
E.
So you need to just go through this table. These are the experimental results and comparisons, right? जैसे current gain सबसे ज़्यादा किसका होगा? Common कलेक्टर या कॉमन एमिटर का, राइट? जैसे एक एग्जांपल दिया था ना मैंने, आईसी का वैल्यू कितना दिया था 98, सो 98 डिवाइडेड बाय 100 इसका कितना आएगा 0.9।
0.98.
आईसी इज 98, आईबी इज 2, तो कितना आएगा इसका 49।
9.
आई कितना दिया था 100, आईबी कितना था 2, सो इट विल बी 50।
50
सो करंट गेन सबसे ज्यादा किसका है? कॉमन कलेक्टर का।
कॉमन कलेक्टर
उससे कम कॉमन एमिटर, और
कॉमन
सबसे
एमिटर
लेस कौन सा है?
Common base.
कॉमन
कॉमन
बेस
बेस कितना आएगा 0.98, मींस ऑलवेज लेस देन यूनिटी। गेटिंग? So similarly, you can just check it out voltage gain, right? So voltage gain, you will get medium for common base as well as common emitter, and for common collector you will get the voltage gain as less than 1. Okay. Similarly, there will be input resistance and output resistance. So just go through these parameters, right? And this phase shift, right? Phase shift I will be explaining when we will deal with the common emitter amplifiers, right?
Okay, sir.
Any problem in this?
No,
नो
sir.
No, sir.
Okay,
No,
okay,
sir.
okay. So, yes, now let us go further and analyze. Okay, now, अभी मुझे ट्रांजिस्टर का बायसिंग करना था, right? So, how many batteries I have used for biasing the transistor in the circuit?
2 batteries.
Simple.
2
2 batteries
batteries.
2 batteries, right? So let us give a simple example. If I want to bias one single transistor, right, I will need 2 batteries, right? Okay. Now, if I want, if there are 4 transistors in the circuit, how many batteries we want?
8 batteries.
8.
Okay. Okay. अभी देखिए आपके मोबाइल फोन में कितने ट्रांजिस्टर्स होते हैं?
पता नहीं सर.
Millions.
हाँ, there are in millions, right? So उसके लिए फिर millions में बैटरी लगेगा क्या?
No, sir.
No, sir.
नो
Right?
सर
एक बैटरी का प्राइस होता है 5,000 रुपीज, राइट? अगर और एक एक्स्ट्रा बैटरी डाल दिया हमने तो कितना, 5,000 तो बैटरी का ही बढ़ जाएगा, तो मोबाइल का कॉस्ट तो बढ़ना ही है, राइट? सो इज दिस द प्रॉपर वे ऑफ बाइसिंग? और सिंपल 2 रुपए का ट्रांजिस्टर, उसको 2 बैटरी से बायस करो, मतलब 5,000 के 2 बैटरीज लग गए हमें एक ट्रांजिस्टर को बायसिंग करने के लिए। सो इज दिस द प्रॉपर वे?
No, sir.
No,
नो
sir.
नो
No, sir.
So we should be able to bias the transistor with only simple one battery, right? That means we are saving, right? One battery, correct?
Yes, sir.
यस
So
सर
there are types of biasing of the transistor where our focus will be, we will bias the transistor by only one battery. Okay?
Yes, sir.
Okay.
Yes,
Yes.
sir.
So we will see biasing techniques tomorrow. Okay, so till that time, what you do, you just go through whatever detail numericals, right, which we have covered today, and then we will just go through that. Okay. So tomorrow we will be covering the biasing techniques. So I will end the lecture 15 minutes before, right? Today, I'm having some what we can say. Tomorrow we can take some time extra. Okay.
Okay, sir.
ओके
Yeah.
सर
sir.
So
Sir, attendance.
हाँ, वो तो देना है ना. Okay, any difficulties in today's lecture?
No, sir.
No,
नो
sir.
सर
No, sir.
So I will just stop recording.